physics has a dirty secret. The most tested, most accurate theory in human history, the one that describes every electron, every atom, every force you've ever felt, is also catastrophically broken. It predicts empty space should contain enough energy to destroy the universe in an instant. It can't explain gravity. It can't account for 95% of everything that exists. We'll visit the vacuum that should have killed us all, the particle that might be its own antiparticle, and the math problem worth $1 million that no one can crack. If you enjoy this journey, subscribe. We're just getting started. Now buckle in. We begin. Here is something your science teacher probably never told you. Everything you have ever touched, your desk, your phone, the air moving through your lungs right now, is not made of stuff the way you think it is. No tiny billiard balls, no solid little spheres bouncing around inside atoms. That picture, the one most of us grew up with, is wrong. And physicists have known it was wrong for almost 100 years. The real picture is stranger. And honestly, it is more beautiful. Imagine the entire universe is filled with invisible fields. Not fields like a football field. Fields like a stretched blanket covering every single point in space, from here to the edge of the observable universe. One field for electrons, one for photons, one for quarks. Each field is everywhere, all the time, even in the places we call empty. Now imagine you throw a pebble into a still pond. The water ripples. That ripple moves outward, carries energy, and eventually fades. An electron is basically that. A ripple, a localized vibration in the electron field. A photon, a particle of light, is a ripple in the electromagnetic field. Every particle you have ever heard of, every building block of matter, is just a disturbance moving through one of these invisible, all-pervading fields. This framework is called quantum field theory, and it is, without any debate, the most accurate scientific theory humans have ever built. Here is how accurate. Physicists used quantum field theory to predict a property of the electron called its magnetic moment. The prediction matched the experimental measurement to within 1 part in 1 billion. That is like predicting the distance from New York to Los Angeles and being off by less than half an inch. No other theory in the history of science has ever come close to that kind of precision. So why does this matter to you right now listening to this? Because this theory, the most successful theory ever written, is also at its core broken in ways that should terrify us. Not broken like a small rounding error, broken like the foundation of a skyscraper has cracks running all the way through it, and somehow the building is still standing, and no one can figure out why. We will get to those cracks. Each one is more unsettling than the last. But first, understand what quantum field theory actually achieved. Before it arrived, physics had 2 separate languages. Quantum mechanics described the very small, atoms, electrons, probability waves. Special relativity described things moving at extreme speeds, close to the speed of light. These 2 frameworks did not agree with each other. When physicists tried to combine them, the math fell apart. Quantum field theory solved that. It merged both languages into one unified framework. And the payoff was enormous. It predicted the existence of antimatter before anyone had ever seen it. It explained how forces work, not as invisible pushes and pulls, but as particles being exchanged, like 2 skaters throwing a ball back and forth and drifting apart as they do it. It built the foundation for everything from MRI machines to the semiconductors inside your phone. The framework was first sketched out in 1927 by a British physicist named Paul Dirac. He was 25 years old. He sat down, combined quantum mechanics with special relativity, and produced an equation so strange it predicted a mirror image version of the electron, a particle with identical mass but opposite charge. At the time, no one had ever seen such a thing. 4 years later, it was discovered. That is the power of this theory. It does not just describe reality. Sometimes it finds reality before reality knows it has been found. And yet, the same man who built this framework spent the rest of his life deeply uncomfortable with it. Dirac called parts of it ugly. He said a theory this uncomfortable with its own mathematics could not be the final word. He was right. And what comes next will show you exactly why. Paul Dirac was not the kind of person who spoke unless he had something exact to say. His colleagues at Cambridge described him as almost alien in his precision. He once went an entire dinner without speaking. When someone at the table said, "It is raining outside," Dirac stood up, walked to the window, looked out, sat back down, and said, "On this side." That was his personality, pure, stripped-down logic, with no room for noise. So when Dirac published his equation in 1927, and that equation predicted something he had not intended, something that made no physical sense to him, he did not celebrate. He worried. Here is what happened. Dirac was trying to solve a specific problem. Quantum mechanics described electrons well, but its equations fell apart when electrons moved fast, close to the speed of light. Special relativity had to be included. Dirac spent months trying to write a single equation that satisfied both, and in early 1928 he cracked it. The Dirac equation was 4 lines of mathematics, that is all. But those 4 lines contained something unexpected. The equation had 2 solutions, not one. One solution described the electron perfectly. The other solution described a particle with the same mass as an electron, but with opposite electric charge. At the time, only 2 particles were known, the electron and the proton. The proton was the obvious candidate, but its mass was wildly different. Dirac spent 2 years trying to explain this second solution away. He couldn't. Then, in 1932, a physicist named Carl Anderson was studying cosmic rays, high-energy particles raining down from space, using a special detector. He photographed a particle curving the wrong way in a magnetic field, opposite to an electron. Same mass, opposite charge. Dirac's equation had predicted the positron, the antimatter partner of the electron, before anyone had searched for it. Anderson won the Nobel Prize for the discovery. Dirac had already won his. But here is the part that stayed with Dirac. His equation had not just predicted antimatter, it had quietly predicted that for every particle in existence, there is a matching antiparticle. Every quark has an antiquark. Every neutrino has an antineutrino. The universe, according to his math, should have been born with equal amounts of matter and antimatter. If that were true, they would have annihilated each other completely and left behind nothing. No stars, no planets, no you. Clearly, something is slightly off in that symmetry. And no one, not Dirac, not anyone alive today, has fully explained why matter won. That asymmetry is the reason everything exists, and it has no satisfying answer inside quantum field theory. Dirac also hated what the theory required to make predictions. Every calculation started producing infinite answers. Infinite energy, infinite mass, infinite charge. Physicists had to develop a workaround, a method called renormalization, which we will get to. And Dirac despised it. He called it a swindle. He said that getting sensible answers by manipulating infinities was mathematically dishonest, and that the theory was hiding something it did not understand about itself. He was not wrong. Renormalization works. But why it is allowed to work remains to this day philosophically unresolved. Dirac spent his later career searching for a more beautiful version of the theory. He never found it. He died in 1984, still convinced that the framework he had helped build was magnificent, but incomplete. What is remarkable is that even in its incompleteness, the theory kept winning. It kept producing predictions that matched reality. It kept finding new particles before experiments confirmed them. It was as though the mathematics knew something the mathematicians did not. And that gap between what the theory predicts and what anyone can explain is exactly where the strangest mysteries live. The next one involves infinities. and the desperate, embarrassing, somehow successful attempt to make them disappear. Picture a periodic table, not the one on your chemistry classroom wall, something deeper. A table that lists every fundamental building block of reality itself. Every particle that has ever existed, every force that has ever pushed or pulled anything, organized into a single framework. That framework exists. Physicists call it the Standard Model, and it is one of the greatest intellectual achievements in human history. Here is what it contains: 17 fundamental particles, 6 quarks, which are the building blocks of protons and neutrons, 6 leptons, which include the electron and the 3 types of neutrino, 4 force-carrying particles, the photon for electromagnetism, the gluon for the strong nuclear force, and the W and Z bosons for the weak nuclear force, and finally the Higgs boson, which sits alone in a category of its own. Those 17 particles, interacting through those 3 forces, account for every atom, every molecule, every chemical reaction, every piece of matter you have ever seen or touched, every object in this room, every star in every galaxy. All of it reduces at the deepest level to combinations of these 17 pieces. The Standard Model was not built in one go. It was assembled over decades, piece by piece, from the 1960s through the 1970s, by dozens of physicists working across multiple countries. Each piece was confirmed by experiment, each prediction held up under scrutiny. And in 2012, the final missing piece, the Higgs boson, was discovered at CERN's Large Hadron Collider in Switzerland, confirming a prediction that had been made nearly 50 years earlier. That is not just impressive, that is extraordinary. A theory written decades before its final piece was found. And the piece showed up exactly where the math said it would. So, why are physicists not satisfied? Because the Standard Model has gaps, serious ones. And the gaps are not small oversights, they are enormous holes that the theory simply cannot address. The Standard Model describes 3 forces. Gravity is the fourth. It is the force you feel every second of every day. It holds the moon in orbit, keeps the atmosphere pressed against the Earth, and governs the movement of every galaxy. And it is completely absent from the Standard Model. The theory that describes everything else has nothing to say about gravity. Another gap, dark matter. Galaxies rotate at speeds that should tear them apart based on the visible matter inside them. Something invisible is holding them together. That invisible something makes up roughly 27% of the total contents of the universe. The Standard Model does not include it, has no candidate for it, no particle in those 17 that could explain it. Then there is dark energy, the force pushing the universe's expansion faster every second, which accounts for roughly 68% of everything, also not in the Standard Model. Add it up. The Standard Model explains roughly 5% of the universe. The other 95% is mystery. And even within that 5%, there are cracks. The theory cannot explain why matter and antimatter are not equal. It cannot account for the mass of neutrinos. It has no explanation for why the constants it uses, the mass of the electron, the strength of forces, have the specific values they do. Those numbers are just plugged in from experiment. The theory does not derive them. It just accepts them. A theory that accepts 17 particles without explaining why those 17, or why those specific masses and charges, is a theory that is missing something deep. Physicists know this. The Standard Model is described by its own creators as a placeholder, spectacularly accurate, spectacularly incomplete. And the next layer down, the mathematical machinery underneath, is where things get truly uncomfortable. In the 1940s, a young physicist from New York started drawing pictures. Richard Feynman was brilliant, loud, and deeply suspicious of formality. While other physicists filled pages with dense equations, Feynman reached for a pencil and started sketching. Lines, arrows, squiggles, little cartoons that looked almost too simple to mean anything important. They meant everything. Those drawings, now called Feynman diagrams, turned out to be one of the most powerful tools in the history of physics. Here is what a Feynman diagram actually is. Imagine two electrons approaching each other. Electrons carry negative charge, so they repel. But how? What actually passes between them to make them push apart? In quantum field theory, the answer is a photon. A particle of light exchanged between the two electrons like a tiny message. Here, take this, now move away. The photon exists for an instant, carries momentum, and transfers the repulsion. The exchange happens too fast to directly observe, but the math describes it precisely. A Feynman diagram draws exactly that exchange. One line for each electron moving through time, a squiggly line between them representing the photon. Simple as a doodle, but each part of that diagram corresponds directly to a piece of a mathematical formula. The lines are terms in an equation. The vertices where lines meet are constants representing the strength of the interaction. You can read the diagram like a map and write down the math just by looking at it. And you can add complexity. What if the exchanged photon briefly splits into an electron and its antimatter partner, a positron, and then recombines before the exchange is complete? Draw that in. What if that loop has another photon emitted and reabsorbed? Add another layer. Each addition is a more precise correction to the final answer. Each layer of complexity pushes the prediction closer to what experiments actually measure. This is how physicists calculated the magnetic moment of the electron to 1 part in 1 billion. They drew increasingly complex Feynman diagrams, hundreds of them for the most precise calculations, and added up all their contributions. The result matched reality to a precision that has never been beaten. But here is where the strangeness creeps in. The particles appearing inside those loops, the electron-positron pair, the photons flickering into existence, are called virtual particles. They are not directly observable. They exist only as mathematical steps between a starting point and an ending point. But they are real enough to affect the final answer. Real enough that if you ignore them, your prediction is wrong. Real enough that the Casimir effect, a measurable force between two metal plates placed very close together in a vacuum, is caused entirely by virtual particles appearing and disappearing in the gap between them. The vacuum, the emptiest space imaginable, is seething with this invisible activity. Every point in empty space has fields constantly flickering, virtual particles constantly appearing and vanishing, energy constantly borrowing itself from nowhere and returning it almost instantly. Feynman knew this was philosophically strange. He was famously quoted saying that anyone who claims to truly understand quantum mechanics does not understand the situation. He was not being modest, he was being precise. The diagrams work, the predictions work. The activity in the vacuum is real and measurable. But what it means, whether virtual particles are genuinely physical things or just mathematical bookkeeping, remains genuinely unresolved. And those flickering vacuums, those fields that can never go fully quiet, lead directly to the single most embarrassing calculation in all of science. What the theory predicts about the energy hiding in empty space, and how wrong that prediction turns out to be, is something no physicist has been able to look away from. In the late 1930s, quantum field theory had a crisis. Every time physicists tried to calculate something using the new framework, the answer came out as infinity. The energy of an electron interacting with its own electromagnetic field, infinite. The mass correction from virtual particles, infinite. Charge corrections, infinite. No matter what they tried to calculate, infinity kept appearing, and infinity is not a useful answer when you are trying to predict the outcome of an experiment. For a decade, the best minds in physics stared at this problem and felt helpless. Some gave up entirely, convinced that quantum field theory was fundamentally flawed and would need to be replaced. Others kept pushing, refusing to believe that a theory so clearly producing correct answers in simpler cases could be completely wrong. Then, in the late 1940s, 3 physicists working independently, Richard Feynman in the United States, Julian Schwinger in the United States, and Shinichiro Tominaga in Japan, all arrived at roughly the same solution. They shared the Nobel Prize in Physics in 1965 for it. The solution was called renormalization, and it works like this. When you calculate the mass of an electron in quantum field theory, you get 2 parts. The first is the bare mass, the electron's mass on its own, before it interacts with anything. The second is a correction from all the virtual particles surrounding it. That correction is infinite. So the total mass you calculate is infinity plus something finite. Renormalization says, stop treating the bare mass as a real physical quantity. Instead, define the actual measured mass, the number you read off in a laboratory, as the thing that matters. Absorb the infinity into a redefinition of the mass. The infinity and the bare mass cancel, leaving behind only the finite measurable physical answer. Do the same for charge. Same for a few other quantities. Every infinity gets absorbed into a redefined physical constant. And once you have done that, once you have renormalized the theory, every calculation you make from that point forward produces finite, sensible, accurate predictions. It works. Spectacularly, the predictions of quantum electrodynamics after renormalization are the most accurate in all of science. But here is the problem that has haunted physicists ever since. Renormalization is a procedure, not an explanation. It works because it is designed to match what experiments already measured. It absorbs the infinities rather than explaining where they came from or why they appear in the first place. Paul Dirac, who started this whole framework, called renormalization a swindle. He said that hiding an infinite quantity inside a redefined constant is not solving a problem. It is papering over one. The infinities arise because quantum field theory, when applied to very short distances, allows virtual particles at arbitrarily high energies to contribute to every calculation. There is no physical cutoff, no built-in limit to those energies. The theory, in its current form, does not know when to stop summing contributions. Renormalization forces it to stop, but it does not explain why stopping is the right thing to do. Freeman Dyson, one of the physicists who helped systematize renormalization, later wrote that the procedure was a dippy process, his words, and that making it rigorous remained an open problem. Decades later, it still is. Renormalization has been placed on more solid ground through a framework called the Renormalization Group, developed in the 1970s. But the deeper question, why does quantum field theory produce infinities at all, and what does that tell us about the structure of reality at very short distances, remains unanswered. And if you think infinities in a calculation are unsettling, wait until you hear what the theory predicts about completely empty space. Before renormalization saved quantum field theory, there was a period when the theory seemed genuinely doomed. The year is 1930. Quantum mechanics is less than a decade old. Physicists are excited, ambitious, and starting to push the theory into new territory. They try to calculate simple things: how light scatters off an electron, how electrons interact with each other at short distances, and almost immediately the math starts breaking. The specific problem goes like this. An electron moving through space is never really alone. The electromagnetic field it carries causes virtual photons to flicker in and out of existence constantly around it. Those virtual photons can briefly transform into electron-positron pairs, which emit more photons which create more pairs. The electron is surrounded by an infinite cloud of this invisible activity. When physicists tried to calculate the energy of this cloud, the self-energy of the electron, they integrated over all possible momenta that these virtual particles could carry. Since there is no obvious upper limit to momentum in the theory, the integral runs to infinity. The energy of a single electron, according to this calculation, is literally infinite. This is not a rounding error. This is the mathematics screaming that something is wrong. What made it worse was that similar infinities appeared everywhere. Calculating the scattering angle between two electrons, infinite. The correction to the mass of a particle from its interactions, infinite. The probability that a photon travels from one place to another without doing anything, also somehow infinite. The theory was producing infinities faster than physicists could find new quantities to calculate. Some of the greatest names in physics declared the theory unsalvageable. Werner Heisenberg, who helped build quantum mechanics, was convinced these divergences signaled a fundamental breakdown of the framework. He proposed abandoning local field theories entirely and starting from scratch with a different mathematical language. Others held on. They noticed something strange. Even though individual calculations produced infinite answers, the differences between calculations sometimes came out finite. The infinities in certain combinations seemed to cancel each other. This was a hint. A deeply uncomfortable hint, but a hint. The breakthrough came when physicists realized that the infinities always appeared in the same places, always attached to the same few physical quantities: mass, charge, a small number of coupling constants. This regularity was the key. It meant the theory had a specific structure to its pathology, and a specific structure can sometimes be fixed. That fix, renormalization, required redefining what mass and charge meant. It required accepting that the bare, unobserved quantities in the equations are not directly physical, and that the physical quantities are the ones measured in labs. Once physicists made peace with that shift, the infinities disappeared, the predictions became finite, and the precision of those predictions was breathtaking. But the infinities never went away in a deep sense. They were managed, not removed. Hidden inside the redefined constants, waiting. And for any theory where renormalization fails, where there are infinitely many quantities that would need redefining, the infinities cannot be tamed. Gravity is exactly that kind of theory. Quantum gravity, when physicists attempt to apply the same methods, produces infinities that cannot be absorbed into any finite set of redefined constants. The infinities multiply without bound. Every order of calculation requires new, different infinities, and there is no end. That failure, the inability to renormalize gravity, is one of the deepest reasons the two greatest theories in physics remain incompatible. But there is something stranger than infinite calculations lurking just below the surface. And it starts with the question of what is actually happening in the spaces we call empty. Empty space is not empty. That sentence sounds like a philosophical riddle, but it is a confirmed, measurable, experimentally verified fact. Quantum field theory says that every field filling space cannot be completely still. It is a consequence of the Heisenberg uncertainty principle, one of the bedrock rules of quantum mechanics. The uncertainty principle says you cannot simultaneously know both the energy of a system and the exact moment you are measuring it. If you try to pin down the energy of a quantum field at a precise instant, the act of pinning it down introduces uncertainty in the energy itself. What that means practically is this: a quantum field at its lowest possible energy state, its vacuum state, is still not perfectly calm. It fluctuates constantly. The field value jiggles around its average, never truly settling. And those jiggles have real consequences. When a field fluctuates above its baseline energy, it can momentarily produce a particle-antiparticle pair, an electron and a positron, for example, from what looks like nothing. These two particles appear, exist for a tiny fraction of a second, and then annihilate each other and disappear, returning the borrowed energy to the field. This happens continuously everywhere in space, even in the most perfectly isolated vacuum you could construct. You cannot directly observe a single virtual particle. By the time you could try to detect it, it is already gone. But their collective effect is measurable. And here is a specific example. Take two flat metal plates, place them in a vacuum, separated by a distance smaller than the width of a human hair, roughly a few millionths of an inch. Between those plates, the space is so tight that certain virtual photons, ones with wavelengths too long to fit in the gap, are excluded. Outside the plates, those virtual photons still appear and disappear freely. That imbalance creates a pressure. The outside of the plates is busier than the inside, so the plates are pushed together by the activity of empty space itself. This is called the Casimir effect, first predicted in 1948 and confirmed in experiments starting in the 1990s. It is real, it is measured, it is caused entirely by virtual particles flickering in and out of existence. Virtual particles also affect the properties of real particles. The electron, for instance, is constantly surrounded by a cloud of virtual photons and virtual positrons that continuously appear, interact with the electron, and vanish. This cloud changes the electron's apparent charge and mass from what a bare isolated electron would have. Every measurement of electron charge and mass in history has measured the electron plus its cloud, not the electron alone. That is precisely why renormalization works. It redefines the physical constants to include the cloud, absorbing the effect of the infinite virtual swarm into a finite, measurable number. This is confirmed physics. Every atom you have ever studied, every electron ever detected, sits inside this perpetual invisible storm. Now here is the question that leads to the biggest embarrassment in all of science. If every point in space has fields that constantly fluctuate, and those fluctuations carry energy, and that energy is real and measurable in things like the Casimir effect, how much energy does empty space actually contain? Quantum field theory gives a very specific answer, and that answer is so catastrophically, absurdly wrong that physicists have been trying to explain it for decades without success. What empty space should contain, according to the math, would not just fill the universe, it should have torn the universe apart before anything could form, before the first star, before the first atom, before the first second of cosmic time. And yet, here we are. Physicists are careful people. They do not use words like catastrophe lightly. So, when the best physicists in the world call something the vacuum catastrophe, and when they describe it as the largest discrepancy between theory and experiment in the entire history of science, it is worth paying very close attention. Here is the problem. We know the universe is expanding, and since 1998, we have known it is not just expanding, it is accelerating. Something is pushing space apart, making the gaps between galaxies grow faster every second. That something is called dark energy, and it acts like a fixed background energy density filling all of space. Physicists can measure it from how the universe expands. The measured value is extremely small, about the energy equivalent of a few hydrogen atoms packed into a space the size of a large living room. Now ask quantum field theory to predict that number. The theory predicts that every quantum field in its vacuum state contributes energy to empty space through its constant fluctuations. Sum up all those contributions, one for the electron field, one for the photon field, one for every field in the standard model, and the theory produces a prediction for the vacuum energy density. That prediction is larger than the observed value by a factor of 10 to the power of 120. To understand how large that is, the number of atoms in the entire observable universe is approximately 10 to the power of 80. The discrepancy between what quantum field theory predicts and what we actually observe is larger than the number of atoms in the universe by a factor of 10 to the 40th power. The prediction is not slightly off. It is not even in the same universe as the right answer. It is the most spectacular failure of a calculation in the history of human science. If the vacuum energy were anywhere close to what the theory predicts, space itself would be so full of energy that it would have expanded at an unimaginable rate in the very first moments after the Big Bang. Galaxies could never have formed. Stars could never have ignited. Matter would have been ripped apart before it had a chance to clump into anything. Something has to be cancelling that predicted energy down to nearly zero. But what? One possibility is that there is a cancellation mechanism, some unknown symmetry that causes the contributions from different fields to cancel each other out almost perfectly. Supersymmetry, which pairs every particle with a partner particle, was proposed as a candidate for exactly this cancellation. If every particle's contribution to vacuum energy were perfectly cancelled by its superpartner, the result could be zero, but supersymmetry, as we will discover later, has not been found. And even if it were, it would need to be broken to give us the universe we observe, and that breaking would ruin the perfect cancellation. Another possibility is that the cosmological constant, the technical name for this background energy, is simply a feature of the universe with no deeper explanation. It just is what it is, like a physical constant selected from a vast range of possible values. Many physicists find this deeply unsatisfying. A theory that says it just happens to be this value is not really explaining anything. The vacuum catastrophe sits at the intersection of quantum field theory and gravity, and solving it requires understanding both simultaneously. No current theory does that. It is not a footnote, it is not an edge case, it is a crack through the middle of our best description of reality, and no one has any idea how to fix it. What comes just beyond this crack is the force responsible for it, and the reason it cannot be handled by the same tools that fixed everything else. Albert Einstein made a mistake. He admitted it. He called it the biggest blunder of his scientific career. And then the universe turned around and made his mistake into the most important unsolved problem in modern physics. Here is what happened. In 1917, Einstein applied his brand new theory of gravity, general relativity, to the universe as a whole. His equations described how space-time curves in response to mass and energy. When he looked at what his equations predicted for the entire cosmos, he found a problem. The equations said the universe should be either expanding or contracting. It could not sit still. At the time, the prevailing scientific view was that the universe was static and eternal, neither growing nor shrinking, just existing in a fixed state. Einstein believed this, and he did not want his equations to predict otherwise. So he added a term to his equations, a mathematical patch, to hold everything in balance. He called it the cosmological constant, represented by the Greek letter lambda. It acted as a kind of repulsive energy spread uniformly through space, pushing outward to counterbalance the inward pull of gravity. It worked mathematically. The universe his equations described was static. Einstein was satisfied. Then, in 1929, the astronomer Edwin Hubble showed that distant galaxies were moving away from us, and the farther away they were, the faster they receded. The universe was expanding. It always had been. Einstein's static universe was wrong, and the cosmological constant, added specifically to prevent expansion, was unnecessary. Einstein removed it from his equations and called the whole episode the biggest blunder of his career. The cosmological constant was abandoned, treated as a historical curiosity, mentioned only as a cautionary tale about letting preconceptions distort your science. For 60 years, that is where things stood. Then came 1998. Two independent teams of astronomers were studying a specific type of exploding star, a Type 1 supernova, at extreme distances. These explosions are bright enough to see billions of light years away, and they all have roughly the same brightness, which makes them useful as distance markers. By measuring how bright they appeared versus how bright they actually were, the teams could calculate how far away they were and how fast the universe was expanding. What they found shocked both teams. The universe was not just expanding. The expansion was accelerating. Galaxies were flying apart faster now than they were billions of years ago. Something was pushing them apart, and that push was growing stronger over time. The simplest explanation was that Einstein's cosmological constant was real after all. Some energy density in empty space, constant throughout the cosmos, acting as a repulsive pressure. The universe was not static. It was being pushed apart by the very vacuum. Both team leaders, Saul Perlmutter, Brian Schmidt, and Adam Riess, shared the Nobel Prize in Physics in 2011. Einstein was right, and wrong, and right again. But here is where it connects back to quantum field theory. The cosmological constant, understood as vacuum energy, should have a value that the theory can predict, and as we just learned, the prediction is wrong by a factor of 10 to the 120th power. The reintroduction of the cosmological constant did not solve a problem. It reframed one. Now, physicists needed to explain not just why vacuum energy existed, but why it was so absurdly smaller than every calculation suggested it should be. Einstein's blunder became a window onto the deepest crack in modern physics. And just beyond that crack stands a force that refuses, completely, to play by the rules. Three forces walk into a room: electromagnetism, the strong nuclear force, the weak nuclear force. They sit down, get along, fit neatly into the same mathematical framework, and together they build the standard model. Gravity does not show up. This is not a minor inconvenience. Gravity is the force you experience constantly. Every step you take, every time the Earth holds you to its surface, every orbit in the solar system, every galaxy cluster bending the path of light, all of it is gravity. It is the most obvious force in daily life, and it is completely absent from the most successful theory of fundamental physics ever built. To understand why, you need to understand what gravity actually is, according to Einstein. General relativity says that gravity is not a force at all in the traditional sense. It is geometry. Mass and energy warp the fabric of space-time itself, and other objects follow curved paths through that warped space-time. The Earth does not pull the Moon toward it through some invisible rope. The Earth curves space-time, and the Moon rolls along that curve the way a marble rolls inside a bowl. This is a beautiful description. It is also confirmed to extraordinary precision. Gravitational waves predicted by general relativity and first directly detected in 2015 matched Einstein's equations almost perfectly. The problem is that general relativity and quantum field theory speak completely different mathematical languages. Quantum field theory requires a fixed, flat background space-time to define its fields. The fields live on that background. They propagate across it. The background does not change. But in general relativity, the background is the thing being changed. Space-time bends and curves dynamically in response to energy. You cannot define a quantum field on a background that is itself bending in response to the field. The two frameworks are built on incompatible assumptions. Physicists have tried, repeatedly, to force a reconciliation. The approach is straightforward in principle. If every other force is carried by a particle, the photon for electromagnetism, the gluon for the strong force, then gravity should also have a carrier particle. That particle is called the graviton, a spin-2 particle that carries gravitational interaction the way photons carry electromagnetic interaction. When physicists attempt to include gravitons in quantum field theory calculations, the result is catastrophic. The calculations produce infinities, the same renormalization techniques that tame the infinities in electrodynamics fail completely for gravity. Each step of calculation introduces new different infinities. There is no finite set of redefined constants that can absorb them all. The theory as applied to gravity is what physicists call non-renormalizable, meaning the infinities cannot be managed. This failure has been known since the 1960s. More than 60 years later, it remains completely unresolved. String theory was developed largely as an attempt to solve this problem. Loop quantum gravity offers a different approach. Both have made progress in certain areas. Neither has produced a confirmed experimental prediction that distinguishes it from alternatives. And there is something philosophically troubling underneath all of this. The two greatest theories humans have ever built, general relativity and quantum field theory, are both extraordinarily accurate in their own domains. They have both been tested relentlessly and have not failed. but they cannot both be right at the deepest level because they contradict each other. Somewhere, at some scale too small for any current experiment to probe, one of them breaks down, possibly both. The theory that replaces them does not yet exist. Something even deeper is missing, and to find it, physicists have had to dream up some of the strangest ideas in the history of thought. Every force in the Standard Model has a messenger. Two electrons push each other apart because they exchange a photon, a particle of light that carries the electromagnetic repulsion between them. Two quarks inside a proton pull toward each other because they exchange gluons, the carriers of the strong nuclear force. The weak force, responsible for radioactive decay, works through the W and Z bosons. Forces in quantum field theory are not invisible pushes and pulls at a distance. They are particle exchanges. Something travels between the interacting objects and delivers the message. Gravity, if it fits into this picture at all, would have its own messenger. Physicists call it the graviton. It would be a massless particle, like the photon. It would travel at the speed of light. And based on the mathematics of how gravity behaves, it would have a specific quantum property, a spin value of 2, which is different from the photon's spin of 1. On paper, the graviton is straightforward to describe. Its properties follow almost immediately from the requirement that the carrier particle reproduce the behavior of general relativity at large scales. The math is clean, the prediction is specific, the problem is detection. The graviton is almost certainly the most undetectable particle that could possibly exist. Here is why. Gravity is by far the weakest of the four fundamental forces. An ordinary refrigerator magnet can hold a paper clip against the gravitational pull of the entire Earth. The electromagnetic force between two electrons is roughly 10 to the 36th times stronger than the gravitational force between the same two electrons. Gravity is vanishingly weak at the particle level. To detect a single graviton, a detector would need to be sensitive enough to register a single quantum of gravitational interaction. Because gravity is so weak, a single graviton carries an almost immeasurably small amount of energy. Physicists have estimated that a graviton detector capable of registering even one graviton per year would need to be so massive, roughly the size of Jupiter, that it would collapse into a black hole under its own gravity before it could measure anything. Some physicists argue that gravitons may be fundamentally undetectable, not just practically difficult to observe. If that is true, it creates a strange situation. We are fairly confident the graviton should exist. The math seems to demand it, but we may never be able to confirm its existence through any conceivable experiment. Gravitational waves, ripples in space-time itself, were detected by the LIGO experiment in 2015. Those waves are a confirmed prediction of general relativity. But gravitational waves are classical phenomena, produced by enormous objects like merging black holes. They carry enormous amounts of energy. Detecting the individual quantum packets of that energy, individual gravitons, is a completely different and possibly impossible challenge. This is one of the strangest corners of modern physics. A particle whose existence we have strong theoretical reasons to believe in, whose properties we can calculate, and which we may never actually detect. A force carrier for the most familiar force we experience, and yet completely invisible to every detector ever built or proposed. And the theories attempting to explain how gravity fits into the quantum world are some of the most ambitious and most contested ideas in the history of science. In the 1980s, the mood in theoretical physics was electric. A new framework had emerged, and the physicists working on it were convinced they were close, maybe years, maybe a decade away, from the final theory of everything. A single framework that would unify all forces, explain all particles, and answer the deepest questions in physics. They called it string theory. The central idea was simple enough to state, but radical in its implications. Instead of treating particles as zero-dimensional points, dots with no size, string theory proposed that every fundamental particle is actually an unimaginably small, one-dimensional string. a loop or an open strand of energy vibrating at different frequencies. Different vibration patterns produce different particles. An electron is a string vibrating another way. A photon is another pattern entirely. The appeal was immediate. When you calculate the interactions of point particles, you get the infinities that plagued early quantum field theory. When you use strings instead, those infinities are naturally smoothed out. The extended size of the string, even though it is fantastically small, far smaller than any current experiment could probe, softens the violent behavior at short distances. And more remarkably, when physicists worked out what vibration patterns strings could have, one of them naturally produced a massless spin 2 particle, exactly the properties the graviton is supposed to have. Gravity fell out of string theory automatically, without being put in by hand. This was extraordinary. For the first time, a framework seemed to offer a genuine path to combining quantum mechanics and gravity. The excitement was enormous. String theory also required something unusual. Extra dimensions. The mathematics only worked consistently in 10 dimensions of space-time, 9 of space and 1 of time. The 3 spatial dimensions we observe are the large ones. The remaining 6 are proposed to be curled up into tiny geometric shapes, too small to detect with any current instrument. These shapes, called Calabi-Yau manifolds, determine the physical constants of our universe, the masses of particles, the strengths of forces. Based on their precise geometry, here is where the trouble began. There are not 1 or 2 possible Calabi-Yau shapes. There are an estimated 10 to the power of 500. Each one produces a different universe with different physical laws. String theory does not tell you which shape is the right one. It does not predict which of those 10 to the 500 possible universes we happen to live in. Every possible version of physics seems to be equally valid within the framework. This proliferation of possible universes became known as the string theory landscape. Some physicists argued it might be explainable through the anthropic principle. We live in a universe compatible with our existence, so of course we observe the constants we do. Others called this unfalsifiable and therefore unscientific. More critically, after 4 decades of intense work, string theory has produced no experimentally testable prediction that distinguishes it from other theories. Nothing in any particle accelerator has confirmed a uniquely stringy prediction. The extra dimensions, if they exist, remain invisible. The superpartner particles that string theory predicts, through an extension called supersymmetry, were searched for extensively at the Large Hadron Collider and not found. String theory may be correct. It may be the deepest description of reality ever written, or it may be a mathematically beautiful dead end. At this point, no experiment can tell the difference. And that silence is deafening. String theory starts with particles and tries to build gravity. Loop quantum gravity starts with gravity and tries to build everything else. The approach is radically different, and so are the problems it encounters. The central idea of loop quantum gravity is this: space-time is not smooth. It is not an infinitely divisible fabric that you can cut into smaller and smaller pieces without limit. At the very smallest scale imaginable, far smaller than a proton, smaller than anything any experiment has ever probed, space-time is made of discrete chunks, individual quanta of space, linked together like the nodes in a mesh. The fabric of reality is a network, and that network has a minimum size. This minimum size is called the Planck length. It is approximately 1.6 times 10 to the negative 35 meters. To give you a sense of scale, a proton is to the Planck length what a football field is to the diameter of a hydrogen atom. It is unimaginably small. Current particle accelerators probe distances that are still roughly 20 orders of magnitude larger than the Planck scale. We have no instruments that can directly see structure at that level. The mathematics of loop quantum gravity describes space as built from these discrete units, called spin networks, and time as advancing in discrete steps. The smooth space-time of general relativity which you would experience sitting in your chair or orbiting a planet, emerges from the average behavior of enormous numbers of these tiny quanta, the same way a smooth liquid emerges from the collective motion of enormous numbers of individual molecules. This approach has a major advantage over string theory. It requires no extra dimensions. It works in the 4 dimensions we observe, 3 of space, 1 of time, and it does not need to introduce new particles beyond what is already known. It also makes specific predictions. If space-time is discrete at the Planck scale, light of different energies should travel at very slightly different speeds, a tiny deviation from perfect relativity that builds up over cosmic distances. Gamma-ray bursts, which release light across a wide range of energies and travel billions of light-years to reach us, could in principle test this prediction. So far, observations have not confirmed any such deviation. The light from distant gamma-ray bursts arrives with energies at the same time, to a precision that rules out many versions of Planck-scale discreteness. This does not rule out loop quantum gravity entirely, but it has constrained some of its predictions. The deeper problem is one of connection. Loop quantum gravity is a theory of space-time itself, but it has not been shown to reproduce the standard model. The familiar particles, quarks, electrons, photons, the Higgs, should emerge naturally from any complete theory of quantum gravity. Loop quantum gravity does not yet have a clear mechanism for producing them. The theory describes space. It struggles to describe the stuff inside space. String theory and loop quantum gravity approach the unification problem from opposite directions and have both made genuine progress in limited areas. Neither is complete, neither is confirmed. Physicists working on one often speak skeptically about the other. And in 2024, a physicist in London proposed something entirely different, an approach so unusual it challenged the fundamental assumption shared by both string theory and loop quantum gravity. Every attempt to unify quantum mechanics and gravity for the past 60 years has shared one assumption, that gravity, like everything else, must ultimately be quantum version. It must be describable in the language of quantum fields, with a particle carrier, superposition states, and all the machinery of quantum mechanics applied to space-time itself. Jonathan Oppenheim at University College London decided to question that assumption. In early 2024, Oppenheim published a theoretical framework that takes a different path entirely. His idea: maybe gravity does not need to be quantum. Maybe space-time is fundamentally classical, smooth and continuous, while everything else in the universe is quantum. And maybe the two can be coupled together through a carefully designed probabilistic mechanism. This sounds simple, but it runs directly into a known problem. Physicists had already proven theorems suggesting that you cannot consistently couple a classical system to a quantum one without creating contradictions. Information would be lost, probabilities would not add up correctly, and the resulting theory would be internally inconsistent. Oppenheim's contribution was to find a specific mathematical structure, a stochastic meaning random and irreversible coupling that threads between these no-go theorems. His classical quantum coupling involves unavoidable randomness built into the connection between quantum matter and classical gravity. The randomness is not a flaw. It is the mechanism, and it can be structured so the mathematical inconsistencies are avoided. The framework makes specific predictions if gravity is classical in the way Oppenheim proposes. The position of a quantum particle should develop a slight, unavoidable fuzziness over time, beyond the usual quantum uncertainty, due to the random nature of the gravitational coupling. This extra fuzziness could, in principle, be tested in ultra-precise experiments involving quantum systems in gravitational fields. No such test has been completed yet. The required precision is at the edge of what current technology can achieve. Experiments to probe this prediction are proposed but not yet run. Oppenheim's framework is highly speculative. Most physicists still expect that gravity will turn out to be quantum in nature. The gravitational wave observations are consistent with general relativity, which is a classical theory, but they operate at scales too large to probe quantum gravity effects. The framework has been criticized for introducing irreversibility in ways that may conflict with other fundamental principles. But what makes it important is not whether it is right. What makes it important is that it is seriously wrong in a specific, testable way, rather than vaguely wrong in an untestable way. It makes a prediction that could, in principle, distinguish it from standard quantum gravity approaches. After decades of theories that predict nothing falsifiable, a speculative idea with a testable prediction is genuinely valuable. Even if Oppenheim turns out to be wrong, the experiments designed to test him might reveal something unexpected about the junction between quantum mechanics and gravity. That junction is one of the most dangerous gaps in all of physics. Dangerous because it is the place where our two greatest theories disagree. Dangerous because everything we have built, from the Standard Model to general relativity, is built around ignoring that disagreement. And the next mystery waiting in that gap is perhaps the most visually dramatic fact in all of particle physics. Here is a fact that sounds impossible. In every experiment humans have ever performed, across every particle accelerator ever built, using every technique ever developed, no one has ever seen a single free quark, not once, in the entire history of particle physics. Quarks are real. They are inside every proton and neutron in the universe. Experiments in the 1960s and 70s showed that when high-energy electrons slammed into protons, they bounced off hard, point-like objects inside, exactly what you would expect if the proton contained small, dense constituents. Those constituents are quarks, and the evidence for their existence is overwhelming. But pull them out, isolate even one, impossible. Every attempt produces the same result. Here is why. Quarks are held together by the strong nuclear force carried by particles called gluons. The electromagnetic force weakens as two charged particles move apart. The further you go, the weaker the pull. But the strong force is different. When you pull two quarks apart, the force does not weaken. It stays roughly constant. The gluon field between the quarks forms a narrow tube of color field. Physicists actually call it a flux tube, that stretches between them like a rubber band. As you pull the quarks further apart, that rubber band stores energy. The further you stretch, the more energy is packed into the tube. And at some point, the energy stored in that tube becomes large enough to rip a new quark-antiquark pair directly out of the vacuum. The rubber band does not snap and release the quarks. Instead, it gives birth to new quarks that immediately pair up with the ones you were trying to separate. You always end up with bound combinations, never with a free quark. The universe appears to have a rule: quarks travel together, or they do not travel at all. This phenomenon is called color confinement, and the color in that name has nothing to do with the color you see. It is a label physicists invented for a quantum property of quarks that comes in three varieties, arbitrarily named red, green, and blue, which must always combine to form a color-neutral object, the same way red, green, and blue light combine to make white. You can never isolate a single colored object. Only neutral combinations are allowed to exist independently. The experimental evidence for confinement is perfect. It has never been violated. Computer simulations using a technique called lattice QCD, which models the strong force on a discrete grid of space-time points, confirm confinement quantitatively and reproduce the measured masses of protons and neutrons with striking accuracy. And yet, there is no analytical mathematical proof that confinement follows from the equations of the theory. The underlying mathematics, called Yang-Mills gauge theory, is the structure on which quantum chromodynamics, the theory of the strong force, is built. The theory clearly produces confinement in simulations, but no one has ever written down a rigorous mathematical proof, starting from the equations of Yang-Mills theory and ending with the result that quarks can never be isolated. This is not a small technicality. This is a gap between what the theory demonstrably does and what mathematicians can actually prove the theory does. And that gap is worth exactly $1 million to anyone who can close it. In the year 2000, the Clay Mathematics Institute in Cambridge, Massachusetts, listed 7 mathematical problems. Each one was described as among the most important unsolved problems in mathematics. Each one came with a prize of $1 million for the first correct solution. 6 of the 7 involves pure mathematics. The 7th involves physics. It is called the Yang-Mills existence and mass gap problem, and it sits directly at the heart of quantum field theory. Here is the background. In 1954, 2 physicists named Chen-Ning Yang and Robert Mills published a generalization of the mathematics of electromagnetism. Electromagnetism is what physicists call an abelian gauge theory, a theory where the symmetry transformations commute, meaning the order you apply them does not change the result. Yang and Mills constructed a more complex version where the transformations do not commute, a non-abelian gauge theory. Their mathematical structure turned out to be exactly what was needed to describe both the strong nuclear force and the weak nuclear force. It became the mathematical backbone of the Standard Model. Yang-Mills theory works. The predictions it produces match experiments to extraordinary precision. The strong force, described by Yang-Mills mathematics, correctly predicts the masses of particles, the behavior of quarks at high energies, and the existence of color confinement in computer simulations. The problem is this: no one has rigorously proven that Yang-Mills theory as a mathematical object actually exists in the way physicists use it. To be precise, physicists define Yang-Mills theory in 4 dimensions of space-time and assume it has a mass gap, meaning the lightest particle in the theory has a strictly positive mass, greater than 0. This is what is observed. Every known particle produced by the strong force has a positive mass. The theory appears to have a mass gap. But proving this rigorously, starting from the mathematical axioms of quantum field theory, constructing Yang-Mills theory in 4 space-time dimensions without approximation, and demonstrating that it has a mass gap, has never been done. The mathematical existence of the theory in full rigor has not been established. This matters because physics and mathematics are using the same equations in different ways. Physicists use Yang-Mills theory through approximation methods, perturbation theory, and computer simulation. These methods produce correct answers when applied to physical problems. But they are not proofs. They are tools. And without a proof that the mathematical object underneath those tools is well defined, there is a possibility, remote, but real, that the foundations are shakier than they appear. The Clay Institute's framing of the problem is precise. Construct a rigorous mathematical framework for Yang-Mills theory in 4 dimensions and prove that the theory has a mass gap. That is the requirement for the $1 million prize. As of 2025, the problem remains completely open. A recent 25-year review of all 10 millennium problems in physics concluded that most remain just as difficult as ever. The Yang-Mills problem is no exception. The closest progress has been made in simplified versions of the theory. Fewer dimensions, different symmetry groups, but the full 4-dimensional, physically relevant version remains out of reach. This is a case where physics ran far ahead of mathematics. The theory works. The math behind the theory is unproven, and somewhere in the gap between those 2 statements lies a mystery about the deep structure of reality itself. What lurks at the edge of that gap changes how you think about the strongest force in nature, and that force, at very different energy scales, does something else that is equally surprising. In 1973, a discovery was made that seemed to flip everything physicists thought they knew about the strong force. Most forces get weaker with distance. Gravity, electromagnetism. The further apart 2 objects are, the less they feel each other's pull. The strong nuclear force breaks this rule completely at large distances, as we just saw. But 2 physicists, David Gross and Frank Wilczek at Princeton, and David Politzer at Harvard, working independently, discovered something surprising at the other extreme. At very small distances, at very high energies, the strong force does not get stronger. It gets weaker, dramatically weaker, as two quarks are pushed closer and closer together. As the energy of their interaction increases, the force between them decreases. At extremely high energies, quarks inside a proton behave almost as if they are completely free, barely interacting at all. This property was named asymptotic freedom, meaning that as you push toward the ultimate extreme of zero distance, the quarks approach a state of complete freedom. Gross, Wilczek, and Politzer won the Nobel Prize in Physics in 2004 for this discovery. Here is why it is so strange. The same force that forms an unbreakable rubber band when quarks are pulled apart becomes nearly invisible when they are pushed together. The coupling, the effective strength of the interaction, runs with energy. At high energy, it is tiny. At low energy, it is enormous. The strong force has a personality that changes completely depending on the scale at which you probe it. This running of coupling strength with energy is not unique to the strong force. All forces in quantum field theory have coupling constants that change with energy scale. This is a general feature of renormalization. But in most theories, the coupling grows at higher energies. Yang-Mills theories based on certain symmetry groups are special. They are the only known theories where the coupling decreases at higher energies. Asymptotic freedom is a rare property. The practical consequences were enormous. Before asymptotic freedom was understood, the strong force at high energies seemed impossibly complicated. The coupling was so large that perturbation theory, the main mathematical tool physicists use, broke down completely. Asymptotic freedom revealed that at high energies, the coupling is small, and perturbation theory works. You can calculate. This opened up an entire regime of strong force physics to precise theoretical treatment. The flip side is the low energy problem. When the coupling is large, when quarks are far apart, as in the outer regions of a proton, perturbation theory fails completely. The mathematics used to make precise predictions at high energies becomes useless. This is why color confinement, which operates in exactly this low energy regime, has never been analytically proven. The mathematical tools that work at high energies are precisely the ones that break at the energies where confinement happens. Lattice QCD, the computer simulation approach, was developed specifically to tackle this regime. It discretizes space-time onto a grid, allows computers to calculate the strong force numerically without relying on perturbation theory, and produces accurate predictions for particle masses and confinement effects. It is the only reliable tool for low-energy strong force physics, but it is a computational method, not an analytical proof. Asymptotic freedom is confirmed physics. It has been tested extensively in particle accelerators, but understanding the full behavior of the strong force across all energy scales, from the nearly free quarks inside a high-energy collision to the firmly confined quarks inside a slow-moving proton, remains a work in progress. And the particle that holds all those quarks together inside a proton, the Higgs boson, it has its own mystery, one that involves the weight of nothing, and a number so absurd it makes physicists question whether the universe was designed to produce life, or whether the word designed means anything at all. Picture yourself trying to walk through a swimming pool. The water pushes back against every step. Your legs slow down, your arms slow down. Moving feels harder than it does in open air. The water is not stopping you. You are still moving, but it is resisting you constantly. And that resistance changes how you behave. Now imagine that resistance is everywhere, not just in water, in empty space itself, in the most perfect vacuum ever created, in the void between galaxies. Everywhere, at every point in the universe, something is pushing back against particles that try to move through it. That something is the Higgs field. The Higgs field is one of the quantum fields we talked about earlier, one of the invisible, all-pervading fields that fill every point in space. But it has one property that makes it unlike any other field in the standard model. Every other field has a value of 0 in its lowest energy state, its ground state. The Higgs field does not. In its ground state, the Higgs field sits at a non-zero value throughout the entire universe. It is always on, always present, always interacting. And particles that interact with it are slowed down. That resistance to motion is what we experience as mass. This is the actual explanation for why particles have mass. An electron has mass because it interacts with the Higgs field as it moves. A quark has mass for the same reason. A particle that does not interact with the Higgs field, like the photon, has no mass at all and travels at the speed of light. The strength of each particle's interaction with the Higgs field determines how much mass it has. This was predicted in the 1960s by a group of physicists, most famously Peter Higgs, working from different angles. The mechanism required the existence of a new particle, a ripple in the Higgs field, the same way a ripple in the electron field is an electron. That particle would be extremely heavy and extremely unstable, decaying almost instantly into other particles after being created. Finding it would require smashing protons together at energies so high that only a machine the size of a city could achieve them. In 2012, after decades of planning and construction costing billions of dollars, the Large Hadron Collider at CERN, a circular tunnel 17 miles in circumference, produced the first confirmed signal of the Higgs boson. The particle existed. It had almost exactly the mass the theory predicted. The final missing piece of the standard model had been found. Peter Higgs and Francois Englert, who had independently developed parts of the same mechanism, won the Nobel Prize in Physics in 2013. Higgs had been waiting nearly 50 years. The discovery was a triumph, but it immediately opened a new problem. The Higgs boson had a specific mass, about 125 times the mass of a proton, and that number, when examined through the lens of quantum field theory, looks deeply, profoundly wrong. The Higgs boson should not be that light. Every virtual particle in the universe, the entire invisible cloud of flickering quantum activity that fills the vacuum, contributes a correction to the Higgs mass. Those corrections push the mass upward toward the highest energy scales in physics. By all rights, the Higgs mass should be around 10 to the 17 times heavier than it actually is. It is not, and no one knows why. That mystery has a name, and it may be the most unsettling fine-tuning problem in all of science. Imagine you are balancing a pencil on its tip. You can do it with enough precision, but you have to work at it constantly. Any tiny disturbance, a breath of air, a slight vibration in the table, knocks the pencil over. The balanced state is not natural. It requires constant, exact correction. Left to itself, the pencil falls. The Higgs boson mass is a pencil balanced on its tip, except the pencil is balanced to 1 part in 10 to the 34th, and no one is holding it. Here is the problem. In quantum field theory, the measured mass of any particle is not just its bare mass. It receives corrections from every virtual particle that briefly interacts with it. For most particles, these corrections are small compared to the particle's mass, so they do not cause trouble. The Higgs is different. It interacts with every massive particle in the standard model, and the corrections to its mass from those interactions are enormous. Specifically, if there is any new physics, any new particles or forces, at energies above what current accelerators can probe, the Higgs mass receives corrections proportional to the square of that energy scale. If new physics exists at the Planck scale, where quantum gravity becomes important, the correction to the Higgs mass is roughly 10 to the 34th times larger than the observed mass. For the Higgs to have the mass we measure, those enormous corrections must be cancelled by the bare mass with almost perfect precision, not approximately, not roughly, to 1 part in 10 to the 34th. A cancellation that precise, happening for no apparent reason, is what physicists call unnatural. Nature tends not to produce accidental cancellations of that magnitude. When you see numbers cancelling to extraordinary precision in physics, it usually means there is a symmetry, a deep structural reason causing the cancellation. The hierarchy problem is the absence of any known symmetry causing this. 1. Supersymmetry was the leading proposed solution for decades. It predicts that every particle in the Standard Model has a partner particle with slightly different properties. The corrections that the known particles contribute to the Higgs mass would be cancelled by equal and opposite corrections from their partners. The cancellation would not be accidental. It would be enforced by the symmetry itself. Supersymmetry also predicted that these partner particles, called superpartners, should be detectable at the Large Hadron Collider. Their masses, to actually solve the hierarchy problem, had to be within a range the collider could reach. The Large Hadron Collider ran for years at the highest energies ever achieved in a particle accelerator. No superpartners appeared. The energy range where they had to exist to solve the hierarchy problem the way theorists hoped has been largely ruled out. This leaves the hierarchy problem without its leading solution. Other proposals exist: extra dimensions that modify how gravity behaves at short distances, composite Higgs models where the Higgs is not fundamental but is built from more basic pieces. But none has experimental support. A small number of physicists have proposed a different kind of answer: the anthropic principle. If there are many possible universes with different physical constants, we necessarily live in one where the Higgs mass allows atoms, chemistry, and life to exist. A much heavier Higgs would change the masses of quarks and electrons enough to prevent stable atoms. So, of course, we observe a light Higgs. Anything else, and we would not be here to observe it. Most physicists find this answer deeply unsatisfying. Explaining a number by saying observers must be able to exist feels like giving up on the search for a real explanation. But after the failure of supersymmetry at the LHC, the landscape of possible answers has gotten much smaller. The Higgs is light. No one knows why. And the next mystery goes even deeper, into a number so suspiciously small that it looks less like a physical constant and more like a message. For 30 years, supersymmetry was the most popular idea in particle physics beyond the Standard Model. It was not just popular because it solved the hierarchy problem, though that alone would have made it important. It was popular because it solved multiple problems at once, predicted a specific class of dark matter candidate, and emerged naturally from string theory. It had the feel of a theory that was trying to be right. The basic idea is a symmetry between two fundamental classes of particles. Every particle in nature falls into one of two categories: fermions, which include quarks and electrons and follow one set of rules, and bosons, which include photons and gluons, and follow a different set. Supersymmetry proposes a perfect mirror between them. Every fermion has a boson partner. Every boson has a fermion partner. The electron has a partner called the selectron. The quark has a squark. The photon has a photino. The gluon has a gluino. These partner particles, collectively called superpartners, would have the same interactions as their Standard Model counterparts, but different masses. And crucially, the corrections they contribute to the Higgs mass would exactly cancel the corrections from the known particles. The hierarchy problem would be solved, not by accident, but by symmetry. Supersymmetry also offered a dark matter candidate. The lightest superpartner particle in most versions of the theory, a neutral particle called the neutralino, would be stable, meaning it could not decay into lighter particles. It would interact via the weak force and gravity, but not electromagnetism, making it invisible. A particle that is massive, stable, and invisible is exactly what the dark matter observations require. Two birds, one theory, plus string theory required supersymmetry to be mathematically consistent in certain forms. The convergence of motivations was hard to ignore. The Large Hadron Collider was, in part, built to find these particles. The accelerator was designed to reach energy scales where superpartners had to appear if supersymmetry was the solution to the hierarchy problem. The search ran for years, producing the most detailed survey of particle collisions at the highest energies ever achieved by humans. The superpartners did not appear. Every search came up empty. Squarks, gluinos, neutralinos, all absent at the energies where they would have solved the hierarchy problem. The mass ranges where the theory was most motivated have been ruled out, not tentatively, but solidly. The data has spoken, and it said no. This does not mean supersymmetry is false. The superpartners could exist at higher energies, beyond the reach of the current collider. But if they are that heavy, they no longer solve the hierarchy problem. The cancellation they provide would be too imprecise to explain the observed Higgs mass. Supersymmetry at high energies might still be mathematically beautiful, might still be part of string theory, but it would no longer be the answer physicists hoped it was. The failure of supersymmetry at the LHC is one of the most significant negative results in the history of particle physics. It did not just eliminate one theory, it eliminated an entire class of solutions to the hierarchy problem. And it left the field searching for new ideas in a landscape that suddenly felt much more open and much more uncertain. The next puzzle in that uncertain landscape is one of the most quietly disturbing in all of physics, a number that should be one thing but turns out to be something else entirely. And physicists are not sure if the universe is hiding something from them, or if they are missing something about themselves. Symmetry is one of the deepest concepts in physics. When a system looks the same after a transformation, flip it, rotate it, swap particles for antiparticles, that is a symmetry. And symmetries in physics are almost never accidental. They point to deep structure. When a symmetry is broken, that also points to deep structure. Physicists pay close attention to both. One symmetry is called CP symmetry, swapping every particle for its antiparticle. P stands for parity, flipping space like a mirror image, so left becomes right and right becomes left. Apply both transformations together, and you have CP symmetry. A theory that obeys CP symmetry looks the same whether you run it in the normal universe or in a mirror universe where all particles are replaced with antiparticles. The weak nuclear force violates CP symmetry. This was discovered in the 1960s and was a stunning result. Nature is not perfectly symmetric between matter and antimatter, at least not as far as the weak force is concerned. The asymmetry is small, but it is real and confirmed. The strong nuclear force, described by quantum field theory through quantum chromodynamics, is mathematically allowed to also violate CP symmetry. The equations governing the strong force contain a term controlled by a parameter called theta bar. If theta bar is non-zero, the strong force would violate CP symmetry in a measurable way. Specifically, it would cause the neutron to have a slight electric dipole moment, a tiny imbalance in the distribution of positive and negative charge inside it. Physicists have searched for this dipole moment with increasing precision for decades. The result is always the same: nothing detected. The electric dipole moment of the neutron is either zero or so small that it is below the detection threshold of any instrument ever built. From this non-detection, physicists have calculated an upper bound on theta bar. The parameter must be smaller than 10 to the negative 11. Written another way, it is smaller than 0.000000001. There is no theoretical reason for it to be that small. In the standard model, theta bar is a free parameter. It could, in principle, take any value from 0 to roughly 6.25. Most values in that range would produce a large, easily measurable neutron dipole moment. But the universe has selected a value that is either exactly 0 or unimaginably close to 0, for no known reason. This is fine-tuning. Extreme fine-tuning. If you picked theta bar randomly from its allowed range, the chance of landing on a value this small would be roughly 1 in 100 billion. Physicists call this the strong CP problem. It is not a paradox in the logical sense. The universe is allowed to have any value of theta bar, including a tiny 1. But a coincidence this extreme demands explanation, and the standard model offers none. The fact that the strong force does not violate CP symmetry, when it is completely allowed to, feels like a clue about something deeper that the theory is not capturing. And the leading explanation for why theta bar is so small involves a new particle that has never been detected, a field that adjusts itself dynamically to zero, and a possible solution to a second mystery at the same time. In 1977, two physicists named Roberto Peccei and Helen Quinn proposed a solution to the strong CP problem. Their idea was elegant and simple in its structure, even if the physics it required was entirely new. The problem was that theta bar, the parameter controlling CP violation in the strong force, was suspiciously close to zero with no explanation. Peccei and Quinn's solution: what if theta bar is not a fixed number at all? What if it is a field, a dynamic quantity that can change its value and naturally relaxes to zero? They introduced a new symmetry into the theory. This symmetry, when broken, as all symmetries in particle physics eventually are, produces a new particle. A particle predicted by the structure of the solution itself. Frank Wilczek and Steven Weinberg independently realized this prediction and named the new particle the axion, after a brand of laundry detergent. The name stuck. The axion would be extremely light, far lighter than any other known particle except neutrinos. It would interact with matter through the strong force and electromagnetism, but the interactions would be so feeble that the axion would pass through almost anything without leaving a trace. It would be nearly invisible to every detector ever built. The Peccei-Quinn mechanism works like a ball rolling down a hill toward a bowl. Whatever the initial value of theta bar, whatever angle the ball starts at on the hill, the dynamics of the axion field cause it to roll down and settle at the bottom of the bowl, where theta bar equals zero. The symmetry of the mechanism forces the parameter to relax to zero automatically, without any fine-tuning required. The strong CP problem is solved not by assuming a specific value, but by building in a reason for the value to become what it is. Then came the second surprise. In the early universe, shortly after the Big Bang, axions would have been produced in enormous quantities through thermal processes and through the relaxation of the axion field itself. They would have spread through the universe, barely interacting with anything, forming a cosmic sea of invisible, nearly massless particles. This is exactly what dark matter does. Axions, if they exist, would be stable over cosmic timescales. They would interact gravitationally and cluster around galaxies the same way dark matter does. Their mass range, while extremely small, falls within windows where they would produce the correct abundance of dark matter observed today. The axion could, in one particle, solve two of the most embarrassing open problems in physics: the strong CP problem and the identity of dark matter. This combination of motivations has driven one of the most sustained experimental searches in modern physics. Experiments with names like ADMX, the Axion Dark Matter Experiment, and Haystack and Abracadabra have been built specifically to detect axion-filled space. If axions exist, they occasionally convert into photons inside a magnetic field, producing a detectable signal at a specific frequency corresponding to the axion mass. So far, no axion has been detected. The searchers have ruled out portions of the possible mass range, but the axion could hide in many other ranges. The experimental sensitivity is improving steadily, and the search is ongoing. The axion remains a candidate. A well-motivated, theoretically attractive candidate for solving two problems at once, but a candidate that has never been seen. That invisibility connects to the next mystery, which operates at a scale so vast it makes particle physics feel intimate. Something is wrong with every galaxy in the universe. When astronomers measure how fast stars orbit around the center of a galaxy, the same way planets orbit the sun, the numbers do not add up. Stars near the outer edges of galaxies move far faster than they should. If the only gravity holding a galaxy together came from its visible stars, gas and dust, those outer stars would be moving too fast to stay bound. They would fly off into empty space. The galaxy would tear itself apart. Every galaxy we have ever observed does the same thing. Every one. The obvious conclusion: there is mass we cannot see, something invisible, distributed in a vast halo surrounding and interpenetrating the visible galaxy, providing extra gravitational pull that keeps those fast-moving outer stars from escaping. That invisible something is dark matter. This idea was first taken seriously in the 1930s, when the Swiss astronomer Fritz Zwicky noticed that galaxies in clusters were also moving too fast to be held together by the visible mass alone. For decades, the evidence accumulated from multiple independent directions: galaxy rotation, gravitational lensing of light around galaxy clusters, the large-scale structure of the universe, the precise pattern of fluctuations in the cosmic microwave background radiation. Dark matter is not a guess. It is one of the most robustly supported inferences in all of astrophysics. Something real and massive is out there, holding the cosmos together. It makes up roughly 27% of all the energy content of the universe. The Standard Model has nothing to say about it. No particle in those 17 fundamental pieces has the right properties to be dark matter. Whatever it is, it does not interact with the electromagnetic force. If it did, it would absorb and emit light, and we would see it. It does not interact with the strong force. It does interact gravitationally, and possibly through the weak force as well. It is stable over timescales comparable to the age of the universe, and it exists in quantities that dwarf all visible matter by roughly 5 to 1. For decades, the leading candidate was a class of particles called weakly interacting massive particles, WIMPs. These would have masses in a range accessible to particle detectors and would interact occasionally via the weak force, producing a rare but detectable signal when one struck an atomic nucleus. Enormous underground detectors, shielded from cosmic rays and background radiation, have been built precisely to catch these rare collisions. The detectors have found nothing, not a single confirmed dark matter signal, despite increasing sensitivity over more than 20 years of searching. The WIMP hypothesis is not completely ruled out, but the most attractive mass ranges have been severely constrained. The search continues, but the optimism that surrounded WIMPs in the 1990s has faded. Other candidates remain: axions, as we just discussed, sterile neutrinos, primordial black holes formed in the early universe. Each has motivated experiments. None has produced a detection. The identity of dark matter is completely unknown. We know it exists. We know roughly how much of it there is. We know where it clusters. We do not know what it is made of, whether it is a single particle or many, whether it interacts with itself, or whether it has any connection to the particles of the Standard Model. 27% of the universe is made of something physics cannot yet identify. And the other mystery hiding in that other 68% is even stranger. In 1998, 2 teams of astronomers were trying to measure how the universe was slowing down. They assumed it was slowing down. The universe began with the Big Bang. Matter was flung outward in all directions, and gravity has been pulling it back ever since. Every object in the universe pulls on every other object. The expansion should be decelerating. The question the teams were trying to answer was, how much? Both teams used the same tool, a specific type of exploding star called a Type Ia supernova. These explosions are remarkably consistent in their brightness, which makes them useful as cosmic measuring sticks. By comparing how bright a distant supernova appeared versus how bright it actually was, the teams could calculate how far away it was and how fast the universes are expanding when that light was emitted. The data came back. Both teams looked at the numbers. Both teams concluded that something had gone profoundly wrong. The distant supernovae were dimmer than expected, not brighter, dimmer. That meant they were further away than the calculations predicted. The universe, instead of decelerating under the pull of gravity, was accelerating. The galaxies were not slowing down as they flew apart. They were speeding up. The expansion of the universe is getting faster. Every second, every galaxy not bound to us by gravity is moving away from us at a slightly greater speed than the second before. The space between galaxies is stretching, and it is stretching faster over time. Something is driving this acceleration, something with negative pressure, a repulsive effect that acts against gravity on the largest scales. This unknown something is called dark energy, and it accounts for roughly 68% of the total energy content of the universe. The simplest mathematical description is Einstein's cosmological constant, the term he added to his equations in 1917 and later removed. The reintroduction of the cosmological constant fits the data precisely. A fixed energy density spread uniformly through space, constant in time, producing a steady repulsive pressure that drives the acceleration. But as we learned earlier, quantum field theory predicts a vacuum energy density that is wrong by a factor of 10 to the 120th power. If the cosmological constant is vacuum energy, why is it so unimaginably smaller than every calculation says it should be? And the cosmological constant as a physical explanation raises its own question. A true constant, something that is exactly the same at every point in space and every moment in time, is philosophically unusual. Why this specific value? Why not zero? Why not larger? Recent data from a telescope survey called DESI has begun to hint that the dark energy might not be perfectly constant. Early results from 2025 suggest that the equation of state of dark energy, the relationship between its pressure and its energy density, may have shifted slightly over cosmic time. If dark energy changes over time, it is not the cosmological constant. It would be a dynamic field, something physicists call quintessence, that evolves as the universe ages. This result is not yet confirmed. The statistical significance is suggestive, but not definitive. More data is needed before anyone can conclude that the cosmological constant is ruled out. But if dark energy turns out to be dynamic, if it has changed over time and will continue to change, then our model of the universe's fate, which currently predicts a cold, endless expansion into darkness, needs to be completely rewritten. What is most remarkable is that 68% of the energy content of everything that exists has no explanation in any current theory. It is the largest thing in the universe, and we have no idea what it is. And some of the smallest things in the universe are turning out to be just as mysterious. For 25 years, the cosmological constant was the answer physicists settled on. Not a comfortable answer, not a satisfying one. The vacuum catastrophe, the mismatch between theory and observation, made it deeply uncomfortable. But the cosmological constant fit the data. The expansion history of the universe matched a model with a fixed, unchanging dark energy perfectly well. And in physics, if something fits the data, you work with it until something better comes along. In 2025, something arrived that might be better, or might be the beginning of something better. The distinction is important, and the physicists involved are being careful not to overstate it. The Dark Energy Spectroscopic Instrument, DESI, is a telescope system mounted at the Kitt Peak National Observatory in Arizona. It is designed to measure the positions and recession speeds of tens of millions of galaxies across a huge swath of cosmic history. By mapping how galaxies are distributed and how that distribution has changed over time, DESI can reconstruct the expansion history of the universe in unprecedented detail. The key measurement is the equation of state of dark energy, a parameter physicists call W. For a true cosmological constant, W is exactly -1. It does not change. If W deviates from -1, or if W changes over time, dark energy is not a cosmological constant. It is something else. DESI's first major data release, analyzed through early 2025, hinted that W may not be constant. The data appeared to suggest that dark energy was slightly stronger in the past and is weakening over time, a behavior inconsistent with a true cosmological constant. The statistical significance of this result was tantalizing. but not conclusive. In physics, a result needs to clear a very high bar before it changes textbooks. Most physicists are treating the DESI result with cautious interest. It could be a real signal of new physics. It could be a statistical fluctuation that disappears as more data comes in. It could be a subtle systematic error in how the galaxy positions are being interpreted. But if it holds up, the implications are significant. A dark energy that changes over time is not a fixed property of empty space. It is a field, something dynamic, something that evolves, something with behavior that must be explained by whatever comes after the standard model. It would rule out the simplest cosmological constant explanation and demand a new theoretical framework. It would also shift the expected fate of the universe. If dark energy is weakening, the accelerating expansion might eventually slow. Galaxies might stop flying apart. In the very far future, timescales almost impossible to comprehend, the universe's fate might look very different from the cold, empty, eternal darkness that current models predict. Or the DESI signal might fade with more data, the cosmological constant might hold, and the vacuum catastrophe will remain exactly as unsolved as before. Physics at the frontier often feels like this. A hint arrives. It could change everything. You wait for more data. The universe keeps its secrets a little longer. What is not uncertain is that dark energy exists. Something is accelerating the expansion, and whatever that something is, it has no home in quantum field theory or the standard model. Just like the invisible mass holding galaxies together, and just like a particle that the standard model specifically said could not exist, and yet clearly does, the standard model made a clear prediction about neutrinos. They are massless, they travel at the speed of light, they carry no rest mass whatsoever. This was not a guess. It was built into the mathematical structure of the theory. The standard model was constructed in a way that did not allow neutrinos to have mass, because adding neutrino mass required introducing new particles or a new type of mass term that physicists at the time had no reason to include. The massless neutrino was a clean, specific prediction of the framework. In 1998, that prediction was proven wrong. The experiment that did it was built inside a mountain in Japan, roughly 1,000 meters underground. The Super Kamiokande detector was a tank filled with 50,000 tons of ultra-pure water, surrounded by thousands of sensitive light detectors. When a neutrino passed through the water and occasionally collided with an atomic nucleus, it produced a faint flash of light that the detectors could record. Neutrinos come in three types, called flavors, based on which charged particle they are associated with: the electron neutrino, the muon neutrino, and the tau neutrino. These flavors are distinct in the standard model, and a massless neutrino of a specific flavor stays that flavor forever. The Super Kamiokande team was studying muon neutrinos, produced when cosmic rays hit the atmosphere above Japan. They measured the number of muon neutrinos arriving from above versus those arriving from below, having traveled through the entire Earth from the other side. The numbers were different. Far fewer muon neutrinos were arriving from below than from above. Somewhere on their journey through the Earth, the muon neutrinos had transformed. They had changed flavor, becoming tau neutrinos that the detector could not see as easily. This transformation is called neutrino oscillation, and it can only happen if neutrinos have mass. Specifically, if two or more neutrino flavors have different masses, quantum mechanics allows them to mix as they travel, cycling between flavors over distance. The oscillation pattern depends on the differences between the mass values. The standard model was wrong. Neutrinos have mass. This is a confirmed Nobel Prize-winning result. Takaaki Kajita of Super Kamiokande and Arthur MacDonald of a Canadian experiment called SNO shared the Nobel Prize in Physics in 2015 for the discovery. The masses are tiny, far smaller than the electron, which is itself light. The exact values are still not precisely measured. What we know is the differences between mass values, not the absolute masses themselves. Whether the lightest neutrino has a mass of nearly zero or exactly zero is still undetermined. More troubling is the question of mechanism. How do neutrinos get their mass? The Standard Model has no natural place for it. Adding neutrino mass requires either introducing right-handed neutrinos, particles that have never been detected, or using a completely different type of mass term called a Majorana mass, which would make neutrinos their own antiparticles. Either option requires physics beyond the Standard Model. The neutrino mass problem is a confirmed crack in the Standard Model's foundation. It does not break the theory in a dramatic way. The Standard Model can be patched to include neutrino mass. But the patch requires new elements that the theory does not explain, and the question of why neutrino masses are so unimaginably smaller than the masses of every other particle remains completely open. What makes this especially strange is that the mathematics of why measurements produce definite results, a question as old as quantum mechanics itself, applies to neutrinos in a particularly vivid way. Here is a question that sounds simple, but has never been fully answered. What happens when you make a measurement? In classical physics, the physics of billiard balls and planets, this question has no interesting answer. A ball is in a specific place. You look at it, you see it. Nothing about the ball changed because you looked. Measurement is passive. Reality exists independently of whether anyone observes it. Quantum mechanics breaks this assumption completely. A quantum particle, an electron, a photon, a neutrino, does not have a definite position, or a definite speed, or a definite spin before you measure it. It exists in a superposition of multiple possible states simultaneously. An electron can be spin up and spin down at the same time. A photon can be in two places at once. These are not limitations of our knowledge. They are features of the physical reality the particle inhabits. The mathematics that describes this superposition is called the wave function. The Schrödinger equation governs how the wave function evolves over time. It is perfectly deterministic. Given the wave function at one moment, the equation tells you exactly what it will be at any later moment. The wave function spreads, interferes with itself, and evolves smoothly. But when you make a measurement, something different happens. The many possible states collapse into one definite outcome. You measure the electron spin and get spin up. The other possibility, spin down, vanishes. The measurement produced a definite result from a superposition of possibilities. The Schrödinger equation does not describe this collapse. It only describes smooth evolution somewhere between the quantum system and the measuring device, and the conscious result, the superposition, became a single outcome. But the mathematical formalism of quantum mechanics, and by extension, quantum field theory, does not tell you when, where, or why. This is the measurement problem. It has been recognized since the 1920s. It has never been resolved. Various interpretations of quantum mechanics have been proposed to address it. The Copenhagen interpretation, favored by many physicists in practice, says the wave function is just a calculational tool and that asking what is happening before measurement is not a meaningful physical question. Measurement is defined as the boundary where quantum becomes classical, and you do not look further. The many worlds interpretation says the wave function never collapses. Every time a measurement could go two ways, both outcomes happen. The universe splits into branches. You experience one branch. The electron in another branch has the other spin. Every quantum event creates a branching, and the universe is an ever-growing tree of parallel realities. Pilot wave theory says particles always have definite positions, guided by a wave that carries information about the entire quantum state. The randomness of quantum mechanics comes from ignorance of initial conditions, not from genuine indeterminacy. Spontaneous collapse theories propose that the Schrödinger equation is slightly wrong, that there is a physical mechanism causing superpositions to randomly collapse, with the probability depending on the size of the system. Each interpretation makes the same predictions for every experiment performed so far. None has been ruled out. None has been confirmed as the correct description. physicists who think about this question seriously often land on completely different answers. Extending any of these interpretations to quantum field theory, to the relativistic multi-particle setting, introduces additional technical complications that remain active areas of research. The universe, at its smallest scale, appears to not have definite properties until something interacts with it and forces a definite result. What that interaction is and what chooses the outcome remains one of the deepest open questions in all of science. And the implications of that question reach all the way back to the beginning of time. Two physicists walk into a room and agree on every experimental prediction of quantum mechanics. Then they explain what those predictions mean. And they disagree on almost everything. This has been the state of quantum foundations since the 1920s. The mathematics works. The interpretations are a battlefield. The Copenhagen interpretation came first, developed primarily by Niels Bohr and Werner Heisenberg in the late 1920s. Its core claim is pragmatic to the point of being almost aggressive. The wave function is a tool for calculating probabilities. Asking what the electron is doing before you measure it is not a valid physical question. Quantum mechanics describes the outcomes of measurements, full stop. The role of the physicist is to set up experiments and record results. The language of classical reality, position, speed, definite properties, applies only to measurement outcomes, not to what exists between measurements. Copenhagen is deeply uncomfortable with questions about reality, independent of observation. Bohr famously said that anyone who is not shocked by quantum mechanics has not understood it. He meant it as a statement of principle, not a limitation. The quantum world simply does not behave the way the classical world does, and demanding it behave classically is a category error. This interpretation dominated physics for decades, mostly because it was practical. You apply the rules, get the right answers, win Nobel Prizes, build transistors and lasers, and do not lose sleep over what reality fundamentally is. It works. In 1957, a physicist named Hugh Everett proposed something completely different. His many-worlds interpretation takes the Schrödinger equation completely seriously and applies it to everything, including measuring devices and the physicists using them. In Everett's picture, the wave function never collapses. Every quantum event that could go multiple ways actually goes all of them. The universe branches. Each branch contains observers who experience a definite outcome because they are inside one branch and cannot access the others. When you measure an electron's spin and get spin up, a version of you in another branch got spin down. Both are equally real. Both versions of you will claim to have gotten a definite result. Both are correct about their own experience. The many worlds interpretation requires no collapse mechanism, which is an advantage. There is no need to explain what triggers collapse or how it works. It also requires an almost incomprehensible proliferation of branching realities, which is either a feature or a fatal flaw depending on your philosophical preferences. More practically, many worlds has a technical problem it has not fully solved. If all branches are real, why do we observe outcomes with the specific probabilities quantum mechanics predicts? Why is spin-up measured 50% of the time when the wave function says equal superposition, not 40% or 60%? Deriving the Born rule, the formula for quantum probabilities, from many worlds alone, without sneaking it in through assumptions, remains genuinely difficult. The debate between these interpretations and others is not resolvable by any known experiment. Both predict identical outcomes for every test ever designed. The question of which is correct is, by current standards, a question about metaphysics as much as physics. What is agreed on by everyone is this: something strange happens when quantum systems interact with measuring devices. The strangeness is real. The mathematics confirms it. What that strangeness means for the nature of reality, whether it means reality branches, or whether reality only exists relative to measurement, or something else entirely, remains the deepest unresolved interpretive question in all of science. The origin of everything we know is wrapped up in exactly this question, and so is the reason anything exists at all. This is the most fundamental question in all of cosmology. Why is there something rather than nothing? At the moment of the Big Bang, matter and energy were created from an unimaginably hot, dense state. The physics governing that creation is, as far as we can tell, symmetric. The same laws that produce matter also produce antimatter in equal amounts. For every quark born, an antiquark should have been born alongside it. For every electron, a positron, matter, and antimatter annihilate when they meet. An electron and a positron collide and produce two photons, pure energy, no mass. If equal amounts of matter and antimatter were created in the Big Bang, they would have annihilated each other completely. Every quark with every antiquark, every electron with every positron, the universe would have been left with nothing but light, expanding and cooling forever into an eternal featureless void. No atoms, no stars, no planets, no you. Instead, here we are. The universe is made almost entirely of matter. Antimatter exists. It is produced in particle accelerators and in cosmic ray collisions, but it exists in tiny quantities and annihilates almost instantly. The observable universe contains structures built from matter, and those structures extend as far as our best telescopes can see. Something was different. The Big Bang produced slightly more matter than antimatter. Not equal amounts, slightly more matter. The excess was tiny, roughly one extra particle of matter for every billion matter-antimatter pairs. The billion pairs annihilated, leaving behind pure light. That one extra particle per billion survived, and those survivors, that 1 in a billion excess, became every atom in every star, in every galaxy you have ever seen or imagined. You are built from the leftovers of annihilation. So is everything else. The question is, why was there an asymmetry at all? For an asymmetry between matter and antimatter to arise from physical processes, the laws of physics must treat matter and antimatter differently. This difference is called CP violation, the same symmetry breaking we discussed with the strong CP problem. The weak nuclear force does violate CP symmetry. Physicists have confirmed this in multiple experiments. But the amount of CP violation in the Standard Model is far too small to explain the observed matter-antimatter asymmetry in the universe. The Standard Model can produce a tiny asymmetry. The universe requires a much larger one. The gap between them is enormous. Some additional source of CP violation, beyond anything in the current framework, must have existed in the early universe. What that source is, and what particle or force produced it, is completely unknown. This is arguably the most important unsolved problem in physics, because its answer explains why you exist. A universe that answered this question correctly would understand the origin of everything. So far, no extension of the Standard Model has provided a confirmed, experimentally supported explanation for baryogenesis, the technical term for the process that produced the matter excess. It remains one of the three great open problems identified by most cosmologists, alongside the identity of dark matter and the nature of dark energy. The universe has kept this secret since the first fraction of a second after the Big Bang, and some secrets are written in particles that should have decayed long ago, but stubbornly refuse to. The proton is extraordinarily stable. You are made of protons. Every atomic nucleus in your body contains them. They have been sitting in your cells, your blood, your bones, without decaying for your entire life, for much longer than your life. The protons in your body are the same protons that formed in the first minutes after the Big Bang, roughly 14 billion years ago. They have been protons for 14 billion years and shown no sign of stopping. And yet most physicists believe they will eventually decay, just not yet. The reason proton decay is expected comes from attempts to unify the three forces of the Standard Model into a single framework. The strong force, the weak force, and electromagnetism have different strengths, but their strengths change with energy. They run, in the language of renormalization. At very high energies, the three coupling constants appear to converge toward a common value. This convergence suggests that at some extreme energy, the three forces are actually one unified force, which fractured into three as the universe cooled. Theories that describe this unification are called grand unified theories, or GUTS. They predict that at the unification energy, quarks and leptons, particles that are completely distinct in the standard model, can transform into each other. A quark can become a lepton, and if a quark inside a proton can become a lepton, the proton can decay. Three quarks go in, lighter particles come out. The predicted lifetime for the proton in the simplest grand unified theories was around 10 to the 31st years. Experiments built to detect this decay, enormous underground tanks of water, shielded from background radiation, surrounded by sensitive detectors, have been watching protons for decades. They have not seen a single proton decay. The non-detection has ruled out the simplest grand unified theory predictions. The lower bound on the proton lifetime established by current experiments is now greater than 2 times 10 to the 34th years. The proton lives at least 10,000 times longer than the simplest gut predictions allowed. This rules out certain theories, but it does not rule out all of them. More complex grand unified theories push the predicted proton lifetime higher, beyond current experimental reach. The search continues, with larger and more sensitive detectors being planned and built. The Hyper Kamiokande experiment in Japan, a successor to Super Kamiokande, is designed with a much larger water tank and improved sensitivity. It could either detect proton decay or push the experimental lower bound even higher, constraining which theories remain viable. If proton decay is ever observed, it would be one of the most significant discoveries in the history of physics. It would confirm that quarks and leptons are connected at a deeper level, provide evidence for the energy scale of grand unification, and point toward the specific gut that describes reality. If it is never observed, if the proton turns out to be truly stable, that would also be deeply significant. It would rule out an entire class of unification theories and force physicists to rethink what connects the forces. Either outcome would teach us something profound about the deepest layer of physical law. For now, the proton sits in underground tanks of water, watched around the clock, stubbornly refusing to die. And beyond the proton, there are objects so extreme that even the laws governing protons break down. Objects where the boundary between quantum mechanics and gravity becomes unavoidable. Objects that may be erasing information, and if they are, one of the foundations of physics is wrong. In 1974, Stephen Hawking discovered something that should not have been possible. Black holes, the objects whose gravity is so extreme that nothing, not even light, can escape from within a certain boundary, were thought to be perfectly black, by definition. Light could fall in, but nothing could come out. The black hole would grow, or sit unchanged, but it would never shrink. Hawking showed that this picture was wrong, and the correction he found created one of the most troubling paradoxes in all of modern physics. Working at the boundary between general relativity and quantum mechanics, using quantum field theory applied to the curved space-time near a black hole, Hawking found that the vacuum fluctuations we discussed earlier behave differently near a black hole's edge. Virtual particle pairs form everywhere, but near the boundary of a black hole, something strange happens. One particle from a virtual pair can fall inside, while the other escapes outward. The escaping particle carries real energy away from the black hole, and that energy has to come from somewhere. It comes from the black hole's mass. Over enormous timescales, a black hole slowly loses mass this way, radiating energy outward in a thermal glow of particles. This is called Hawking radiation. A black hole the mass of our Sun would take roughly 10 to the 67th years to evaporate completely, but it would evaporate. Here is the paradox. The Hawking radiation is thermal. It is random, like the heat from a warm object. It carries no information about what fell into the black hole. An elephant? A library? a computer. All would produce identical Hawking radiation. All the specific information about what was inside would be lost when the black hole evaporated. Quantum mechanics forbids this. One of the foundational principles of quantum mechanics, called unitarity, says that information is never destroyed. The quantum state of a system at any time can in principle be reconstructed from the state at any other time. Information can be scrambled, hidden, spread across many particles, but it cannot simply cease to exist. The universe keeps records of everything. A black hole that evaporates via thermal Hawking radiation and destroys the information about its contents would violate unitarity. Quantum mechanics would be wrong in the presence of gravity, or general relativity would need modification near the end of black hole evaporation, or Hawking's calculation was missing something essential. Physicists have debated this for 50 years. Hawking himself changed his position multiple times. The current majority view, informed by work from string theory showing that black holes can be described as quantum systems, is that information is preserved. The Hawking radiation must carry information somehow, in subtle correlations between emitted particles that look thermal but are actually not perfectly random. How exactly this happens, what physical mechanism preserves the information, and how it escapes from inside a black hole, remains completely unresolved. The boundary between inside and outside a black hole, called the horizon, is supposed to be a gentle place where nothing dramatic happens locally. Hawking radiation suggests otherwise. Recent theoretical work involving structures called firewalls proposed that the horizon might actually be a violent, high-energy boundary that burns anything crossing it, preserving information by destroying it before it can be trapped. No consensus exists. The paradox sits precisely at the intersection of the two theories that refuse to unify, quantum mechanics and gravity, and its resolution may require exactly the unified theory that no one has yet built. There is a final strangeness waiting beyond this intersection, one that concerns not just one universe, but possibly an unimaginable number of them. Here is a number, 10 to the power of 500. Write it out, and it would take more digits than there are atoms in the observable universe to represent. It is not a number that human intuition can hold. It is not a number that any physical quantity in our universe approaches. It exists in one context in modern physics, and that context changes how you think about everything else. It is the estimated number of possible vacuum states in string theory, the number of different possible universes with different physical laws that the theory allows. String theory requires 6 extra dimensions of space, curled up too small to detect. Those extra dimensions must be folded into specific geometric shapes, the Calabi-Yau manifolds we mentioned earlier. Different folding configurations produce different physical constants. A different folding produces a different electron mass, a different strength of electromagnetism, a different cosmological constant. Each configuration is a different version of physics, and string theory contains roughly 10 to the 500 of them. This proliferation is called the string theory landscape, and it creates a profound philosophical problem. Physics has always sought unique predictions. Given the laws of nature, here is what must happen. Here is the specific mass of the electron. Here is the precise value of the cosmological constant. These values are what they are because the laws demand them. If string theory has 10 to the 500 possible versions of physics, it predicts nothing specific. You cannot derive the electron mass from the landscape. The landscape contains universes with every conceivable electron mass. You cannot predict the cosmological constant. The landscape contains every conceivable value of it. Unless, and this is where things become deeply controversial, you invoke the anthropic principle, most of those 10 to the 500 universes would be hostile to life. A cosmological constant even slightly larger than ours would have expanded space so fast that no galaxies or stars could form. A slightly different electron mass would prevent stable atoms. Life requires an extremely specific set of physical constants. If all 10 to the 500 universes exist, as part of a larger multiverse, then we necessarily find ourselves in one compatible with our existence. We do not need to explain why the constants have their specific values from within physics. We exist in the pocket of the landscape where life can exist, and the anthropic principle explains the rest. This reasoning produces deep disagreement. Many physicists consider it a surrender. If you can explain any physical constant by saying intelligent observers must be able to exist, you have explained nothing. You have just found a philosophical reason to stop asking. A theory that cannot, even in principle, make a unique prediction that can be tested is not science. It is storytelling. Others take the landscape seriously as a genuine physical possibility. Some cosmological models produce inflation, the rapid early expansion of the universe, and inflation naturally creates enormous numbers of causally separate regions, each potentially settling into a different vacuum state. The multiverse may be real, and the landscape may be the theory describing it. The tension here is not just between two theories, it is between two philosophies of what science is allowed to say. Whether the landscape represents the future of physics or its abandonment is a question physicists are still fighting about. What is clear is that the landscape was not what anyone hoped string theory would produce. The goal was a unique prediction. The result was an ocean of possibility. And swimming somewhere in that ocean, or perhaps outside it entirely, is the answer that would change everything. We have traveled far, from the invisible fields that replace the idea of particles, through infinities that should have broken a theory but somehow make it more accurate, through a vacuum that should contain enough energy to destroy the universe, and somehow does not, through gravity that refuses to join the quantum world, through quarks that can never be separated, through a Higgs boson that is impossibly light, through dark matter holding every galaxy together and dark energy accelerating everything apart, through neutrinos that broke the Standard Model's prediction, through matter that should not exist, and protons that refuse to decay, and black holes that may be erasing the universe's memory. Each one of these mysteries is not an isolated puzzle. They are connected. Solving any one of them would likely pull on threads that reach into the others. Consider the vacuum catastrophe. Explaining why the vacuum energy is so small would require understanding how quantum fields and gravity interact at the most fundamental level. That understanding would be quantum gravity, the unification that has escaped physics for 60 years. Quantum gravity would in turn explain why renormalization fails for gravity and might explain what happened in the very first instant after the Big Bang, which is when matter-antimatter asymmetry was established. Pull on one thread, and the whole fabric shifts. Or consider dark matter. If a new particle is discovered that accounts for the invisible mass in galaxies, it would be a particle that the Standard Model did not predict and cannot accommodate. Its properties, its mass, its interactions, its relationship to known particles would be clues pointing toward whatever comes after the Standard Model. The theory that explains dark matter would likely also have things to say about why the Higgs is so light, and possibly about the strong CP problem. A single discovery could unlock a cascade. Or consider the measurement problem. Most physicists treat it as a philosophical inconvenience and move on. But if a physical collapse mechanism were discovered, something that genuinely explained why superpositions become definite outcomes, it would be a new piece of physics that quantum field theory does not contain. That new physics would need to fit into the framework of relativity, and its implications might reach into cosmology, into the nature of time, into what happens inside black holes. The mysteries are not separate rooms, they are corridors connecting the same house. What would solving these problems mean for you, practically? The history of physics suggests the answer is things you cannot currently imagine. Electromagnetism was once a curiosity of sparks and lodestones. Understanding it produced electricity, radio, television, every digital device in your pocket. Quantum mechanics was once purely theoretical. Understanding it produced semiconductors, lasers, the entire digital world. General relativity was once an abstract mathematical structure. Understanding it now runs the GPS satellites. that guide navigation. The physics hiding behind the standard model's failures is inaccessible with current technology, but the technology built from understanding it could be as far beyond our current world as a smartphone is beyond a candle. Energy from processes we cannot yet engineer, materials with properties we cannot yet predict, communication or computation based on quantum principles we have not yet understood. Or the answers may arrive and show us that some of these mysteries have no technological application, that they are simply facts about the deep structure of reality, discovered for their own sake, because human beings look at the sky and the atom and cannot stop asking what is actually there. That impulse, the refusal to accept incomplete answers to the deepest questions, is what built every equation in this series. It is what Dirac felt when his equation predicted antimatter he did not believe in. It is what the Super Kamiokande team felt when their numbers showed neutrinos changing flavor. It is what both supernova teams felt when their data said the universe was accelerating, and they almost did not believe it. The questions are still open, the people asking them are still out there, and the universe, patient and indifferent, holds its answers just a little further beyond the current edge of what we know.